Ok, 1, 2, 3. All right, good morning. We'll start. Okay, so today we'll continue talking about probabilistic reasoning. So last week, if you remember, I've introduced the topic of probabilities, and for us, the reason I introduced this framework was that at some point what we want to do is to maintain beliefs about things we know we don't know about the environment, okay? And the proper way to do that, and that's something we can even show mathematically, is that if you want to encode beliefs as numbers, then probabilities following Kolmogorov axioms is the thing to do, okay? So that's what we did last week. Then we introduced various concepts, which you should already be familiar with, like probability distributions, joint distributions, marginal distributions, conditional distributions. We've also talked briefly about inference, and also about assumptions that we can make between variables to reduce the size of the representation of probability distributions. Okay, we've talked about statistical independence. We've also been talking about conditional independence. So today we'll continue on this topic, but we'll focus more on inference and then on parameter learning. Okay? So the menu for today will be first Bayesian networks, which will be a way to represent probability distribution compactly. And so I will introduce the notations and then various things we can do on top of that. This formalism, the formalism of Bayesian network, is something I will reuse over and over in the remaining lectures, and more specifically next week when we talk about, or next time when we talk about probabilistic reasoning over time. Then we'll talk about two inference algorithms that we can use to produce exact results. To be honest, I'm giving them to you just for your information, because in practice they are completely useless for reasons I will also elaborate on. And finally, we'll see how we can learn probability distributions. That's the very first time we'll be talking about machine learning in some sense. So I will talk about parameter learning, which is also something then which we'll reuse in the 7th lecture when we talk about neural networks. Okay? So that's the menu for today. All right. So first thing, Bayesian networks, which is something we can use to represent knowledge when our knowledge is uncertain. Okay? So if you remember, we've already discussed the fact that if you represent a joint probability distributions as a table, okay, if you have n variables, each of them can take a certain number of values, then the number of rows that you would need in this table is exponential in the number of variables. Okay, so that's not very practical nor useful, because in most cases we'll not even be able to instantiate this table. Okay, or if we can, we'll still be hit by the size of this table when we want to do inference, because usually then the inference will be proportional also to the number of rows, meaning exponential also in the number of variables. Okay? And last week, I've said that if we make additional assumptions like independence or conditional independence assumption, then we can basically reduce the number of just numbers, probability values that we need to represent the same distribution. Okay? What I will do now is to basically do the same thing, but show you that we can represent these assumptions in the form of a graph, so a diagram which will encode all these assumptions that we are making between variables. Okay? So the concept I want to introduce now is the one of a Bayesian network. So Bayesian network is something not too complicated to understand. it's a representation of joint probability distributions over one or several variables. So in this case, here, you would have the Bayesian network representation of a probability distribution defined over 6 random variables, L, R, T, B, T prime, and D. Okay? So each node in this graph, which is a directed acyclic graph, you see that two nodes may be connected, and when they are connected, the connection is directed. Okay? It goes from a parent to a child node. Each node in these diagrams will correspond to a random variable. Okay? These random variables, for us, they will be either observed or unobserved. Okay? If you remember last week, I've been talking about hidden variables, things we assume are part of the system, but unfortunately we don't see. And on the other hand, we may have evidence variables, observations, so variables for which we'll get access to their values. Okay? So these random variables, they can be observed or unobserved, and also they can take any kind of values. So they can be discrete, that's what we'll assume today as well, but they can also be continuous. Okay? That's something we'll use next week already, continuous variables. Then an edge connecting two variables indicates a direct probabilistic dependency between two variables. Okay? I will not elaborate too much on what exactly I mean yet about probabilistic dependency, but basically it means that there is some kind of probabilistic relationship going from one to the other. Okay? What is also important is that in these Bayesian networks, so let me just reproduce it here. And each node is also labeled with a conditional probability distribution. Okay? By that I mean, for example, if you take this node R, which corresponds to the random variable R, then I will also say that together with this node comes a conditional probability distribution, which in this case would be the conditional probability distribution that defines the values and the probability associated to these values that the variable R can take given its immediate parents. So in this case, given L. Okay? So together with the node, we have this table, this conditional probability distribution. Okay? Similarly, here we would have associated with the T variable the conditional probability distribution of T given its immediate parents, so R and B. But there are also a few nodes for which we don't have any parents, but that's fine. We just have a marginal distribution, for example, for L over the values of that variable. Okay? Okay, so these labels are probability distributions of the kind that we have seen last week. Marginal distribution, conditional probability distribution, whatever. Okay? So each node xi formally will be annotated with a conditional probability distribution, which I will denote as P, bold P, of the random variable xi given its parents. Okay? So to give you an example, the illustration I will use today, and that's also the one which is used in the textbook, is the case of a scenario in which you imagine that, okay, you have an alarm at home and it rings, okay? But you are not home, but your two neighbors are at their own places and they give you a call, okay? So you want to represent this scenario as a Bayesian network, as a probability distribution. And what you could do is to model this scenario using 5 variables. So of course you have a variable for the alarm, whether or not it's actually ringing. Then this alarm could be caused by several factors. For example, there is a burglar in your house. Okay? Or it could be that the alarm went on for other reasons, like there was an earthquake close to your place. Okay? And that also could trigger the alarm. And then we can add two more variables. One, let's say for John, whether or not he calls you, and another for Mary, your other neighbor, whether or not she calls you. Okay? And so in this scenario, we can define a Bayesian network, and we can define its topology, so how we organize the nodes and how we connect them, simply by following domain knowledge. So for example, a burglar could set the alarm off, an earthquake could also set the alarm off, the alarm could cause Mary to call you, and also the alarm could cause John to call you. Okay? So that means we could, for example, draw the corresponding Bayesian network, or a corresponding Bayesian network, in which you would have, let's say, 5 variables. One for the burglar, let's call it B. Another for the earthquake, let's call it E. Then for the alarm, let's call it A. Then, from domain knowledge, it seems easy to define a probability distribution associated to the alarm, given either a burglar or the earthquake. Okay? And then, given the alarm, it seems also easy to define the conditional probability distribution of John calling you or Mary calling you. Okay? And so, for again, together with these 5 random variables, we would have conditional probability distribution that we associate to each of them. So here we would have PB, here we would have PE, here we would have P of A given B and E. Here we would have P of J given A. And finally, P of M given. All right? So that's what you have also here in this slide. We have these 5 random variables with their full name. And you also see the conditional probability distribution that we associate to each of those. All right? Do you have questions on this? Now, what I'm claiming is that this representation of the scenario actually represents, without any loss, the full joint probability distribution of the 5 random variables together. Okay? And we can show that quite easily. So what will happen is that a Bayesian network implicitly encodes the full joint, okay? And it will do so as a product of local distributions. All right? So what I'm claiming is that the joint distribution over the n random variables in your Bayesian network is equal to the product of the marginal conditional distribution associated to each node, given their immediate parents. Okay? If you multiply all these conditional distributions together, what you obtain is the joint distribution over all the random variables. Okay? So how can we prove that? Well, by the chain rule, we know that if we have n variables and a distribution over n variables, we can always factorize this joint as a product over n factors going from 1 to n, where each of these factors is the conditional distribution of the ith random variable, so p of xi, given all the previous variables in the ordering. Okay? So that's something you can do, and you can do so actually in any order that you want. So that's a fact. Then, provided that we assume that we have conditional independence assumption of xi with its predecessor in the ordering given its parent, and provided that all the parents of xi appear before in the ordering that we pick, okay, then we have that, for example, the term I, so p of xi given x1, x2 up to xi minus 1, then given these assumptions, this will be the same because of the conditional independence assumptions and the fact that we assume that all the parents appear before, then we'll have that p of xi given all the previous variables can be simplified to P of xi given its parents and its parents only. Okay? So that means we can just rewrite each one of those factors using this simplification, and what we'll have is that the joint is equal to the product of the conditional distribution of the variables given their parents. Okay? So this is convenient because, but that's the same reason, this is exactly the same as what I've explained last time. Instead of representing, for example, here a joint distribution over 5 variables using, I don't know, at least 2 to the 5 numbers, we can just store these smaller conditional probability distributions, and in total we'll have much fewer numbers than what we would have to use to represent the joint directly. Okay? So in this case, we would need 1, 2, 3, 4, 5, 6, 10 numbers instead of 32. Okay? What is also convenient with a Bayesian network is that once it's instantiated, you can use it to retrieve the probability value of any joint event. So for example, if you want to retrieve the joint probability value of John calling you and Mary calling you and the alarm going on, but there was no burglar and no earthquake, what's the probability of this event? Well, you just have to read off the corresponding values in the probability distribution that you associate to each node. So in this case, you would so let's start maybe from the variables at the top. So the query is P of J M A not B. Are you familiar with this symbol? It just means not, okay? So this would be, so I assume that all the variables are Boolean, so they can be either true or false. Okay, when they are true, I will just denote that with the corresponding lowercase letter. So for the J variable, I would assume this is the positive value, and this would be the negative value. Okay? All right, so this can be read from the structure of the Bayesian network. So we would have that this is equal to P of node B times P of node E times P of A given node B, node E times P of J given A times P of M given A. Okay? And each of those probability values can be read directly from those tables. Okay, so here in the table, since it's Boolean, we only show the value associated to the positive value, and the probability of the other value is simply the complement of the probability. So P of node B in this case would be 1 minus 0.001, so that's 0.99 node B times P of node E times P of A given node B and node E. In this case, that corresponds to the last row of the table, so that's 0.01. So in which we say the probability that the alarm goes on if there is no burglar or no earthquake is not 0, but it's a very small number, 0.001. Then the probability of John calling you if there is an alarm is given by this entry, the first. And finally, the probability that Mary calls you if there is an alarm is 0.7. Okay, then you multiply all these numbers together and you get the joint probability value of this combination of realizations for the variables. Okay, and you should get this number. Okay, so this was the first example of a Bayesian network. We can also use the same representation to represent, if you remember, this dentist scenario that we considered last week. So this scenario also can be modeled as a Bayesian network with 4 variables. So the weather variable, then a cavity variable, a toothache variable, and a catch variable. Okay? And here you see that the weather variable is not connected to any of the other variables. Why is that? Yes?
Events are independent.
Uh-huh.
So it doesn't influence any of the range.
Okay, what do you mean by influence?
The probability, conditional probability of the two is conditioned by the weather, the same as the itself. And so
Yeah. So what happens is that because exactly what you said, because we've assumed and we've said that the weather was independent of any of the other 3 variables, we could add these connections if we wanted, okay? But they would be completely useless because of the assumptions that we make. Okay? Because we assume that P of weather given, let's say, a cavity is the same as P of weather. Okay? So there is no, in a sense, influence of the cavity variable on the weather. Right? And so, as I said there, by construction, the topology of the network will encode conditional independence assertions. So that's a very important statement. When you see or when you draw a Bayesian network, what you are also making explicit are the conditional independence assertions. Okay? So, and what I mean precisely by that is that the edges that you don't draw will correspond to your conditional independence assumptions. Okay? So in this case, the fact that we don't connect weather to any other variable means that we are making these conditional independence assumptions. Okay? And it's not because you make an edge that necessarily you will have 2 variables that are dependent. Okay? Okay, let's take another example, maybe a bit more concrete. Let's say we have 2 variables, rain and traffic, okay, R and T. And so you have these 2 variables, and we want to define the joint probability distributions of these 2 variables together, okay? So we want to define the joint probability distribution of joint events about the rain and traffic, okay? So one possible Bayesian network that we could draw is this one. First, the rain variable, and then second, connected to it, a traffic variable. Okay? So obviously, they are dependent. If there is rain, then it's more likely that there will be traffic on the road. Okay? So that could be modeled by using this Bayesian network together with these 2 conditional probability distributions that we associate first to the rain variable. So we would have the marginal distribution of the rain. Okay, and we would say, for example, that the marginal distribution, the marginal probability of the rain is 0.25. Okay, and so the complement, the probability of no rain, would be 0.75. Okay, and then we define, because that's a Bayesian network, we associate to T the conditional distribution of T given its immediate parents, in this case given R. And so we would have to define P of T given R. Okay? And so we could just enumerate all combinations of these 2 variables. So first we would have there is rain. So what is the probability of traffic? So the positive value for T. given that it's raining, and we could say that in this case, the probability of traffic given rain is 0.75. Okay? That's just knowledge that we encode in the rows of this conditional probability distribution. You could similarly say that the probability of no traffic given rain is 0.25, and that's what we should do because these numbers, they must sum to 1. Then we would also define what is the probability of traffic if there is no rain. So in this case, let's say 50%. And the complement, the probability of no traffic if there is no rain, would be 50%. Okay? So that seems very intuitive. So, and we can use Bayesian network to represent these relationships. However, these edges, they are a bit misleading because they do not need to be causal. You can represent exactly the same joint distribution over our two variables using this other Bayesian network in which first we have the traffic variable and then second, as a child node, the rain. Okay? And so the probability distribution that then we could define would be that the marginal probability of traffic, let's say if there is traffic, it's 9/16, and if there is no traffic, it's 7/16. And then if we say that the conditional probability distribution of the rain given traffic is defined by this table, so the probability of rain given traffic is 1/3, the probability of no rain given traffic is 2/3, probability of rain given no traffic is 1/7, and the probability of no rain given no traffic is 6/7. So if you look at this Bayesian network and this one, who thinks they do represent the same joint probability distribution? Raise your hand. 1, 2, almost. Who thinks they do not represent the same joint probability distribution? 1, 2, 3, 4. Okay, let's see. So they would or wouldn't represent the same probability distribution if when you multiply these two matrices, these two probability distributions together, they give you distinct values. Right? Oops. Okay. So let's see. For example, what is, according to this first version of the Bayesian network, what is PR, so positive for traffic and, no, positive for rain and traffic. So we just have to read. So according to this Bayesian network, that's something we can write as PR times P T given R, right? Now, what is PR? It's given, so let's write it as 1/4 times 3/4. That's 3/16. Okay? Now, if we take the other Bayesian network, this one, where we have flipped the two variables, we have that PRT is defined as P of T given times, R given T. Okay? And the values, the probability values, we can just read them from the table. So P of T, the marginal probability of traffic, is 9/16. And the conditional probability of rain given traffic is 1/3. Okay? So this becomes 3/16. You can compute the 3 other combinations of the 2 variables, and you will see that we get exactly the same joint probability values. Okay, so that means these 2 Bayesian networks, even though they are different, they both represent the same joint probability distribution. Okay, so please do not interpret these edges, these arrows, as some causal connection going from the first to the second. Okay, you may build and design your Bayesian network such that these edges will also correspond to causal relationships, but you don't have to. Okay? That's a counterexample. Okay, so really the only thing which is made explicit when you build these Bayesian networks are the conditional independent assumptions which you encode in this diagram through the edges that you don't put in the diagram. Okay? That's the only thing which is explicit in these Bayesian networks. All right, so now that we've seen these examples, how do we build a Bayesian network? Well, the recipe is simple. You can follow this algorithm. So first, you choose your variables. Okay, you are modeling some system. You define the system through a bunch of variables. And step 1, you pick some ordering of the variables. So you say variable B is the first, variable E is the second, variable E is the third, J is the fourth, and M is the fifth, for example. Okay? So you impose some ordering, which is completely arbitrary. That's something you choose. And then what you do is that you repeat these 4 steps. You add xi to the network. So if you have I going from 1 to n, you add xi to the network. So you draw your node xi. And then you select a minimal set of parents in the among the variables that we have already added to the Bayesian network, such that P of xi given all the variables from 1 to xi minus 1 is equal to P of xi given this minimal set of parents. Okay? And then for each parent, then you insert simply an edge, a link from the parents towards that node. Okay? And finally, you just write down the conditional probability table, so this table together with it. Okay? And so if we follow this algorithm, and if we take the burglar, earthquake, alarm, John and Mary scenario, we could draw this diagram. Okay? But if we pick another ordering for the variables, we could obtain other Bayesian networks. Okay? And so, for example, if you decide to order the variables, first it's Mary, then John, then alarm, then burglar, then earthquake, okay, you would obtain this Bayesian network on the left. If you pick yet another ordering, Mary first, then John, then earthquake, then burglar, then alarm, you would get yet another Bayesian network. Okay? What is important is that these 3 instances of the joint distribution in the form of Bayesian networks, they are the same in a sense. All 3 represent the same joint distributions. However, of course, they are not equal. These 3 Bayesian networks are not equal because some are more compact than others. Okay, if you count the number of probability values you need to store in total at the nodes, okay, there will be Bayesian networks for which you just have a few numbers to store, and maybe, for example, in this version, the number of probability values you would need to store is close actually to the size of the joint probability table. Okay, so it'll be close to exponential. Okay. you have questions so far on this? Okay, so just to recap, I'm just introducing Bayesian network as a way to represent probability distributions, joint probability distributions, where the nodes will correspond to variables, edges to probabilistic relationships, but truly what matters are the edges that you don't have between nodes. These correspond to conditional independence assumptions. And already what I've told you is that there might be several Bayesian networks that do represent the same joint distribution. They are not equal. Some may be more compact than others, depending on the ordering of the variables that you choose when you build the network. Okay? And of course, one thing that could be interesting is to try to recover the most compact representation, but that's a difficult problem. All right. So let's assume that we are given a Bayesian network, for example, one of these two. There are questions that you can answer, and usually questions about independence relations, just by looking at the topology of the network. So, for example, could you tell me, for the left network, so this one, if J, what's going on? If J and M are independent. Oh, yes.
No,
What?
because there's an edge between them.
Okay.
But if we just look at the graph, if we don't take the checks from fireflies above, they are not independent.
Okay. That's almost correct. Actually, you can't answer this question. Because it depends also on the content of the probability table associated to J. You could still have two independent variables that you connect, and then there will be values in the CPT which will be such that it's just the same as having J and M. So in this case, maybe not. That depends on the content. What about so can you tell me if we have that for the left network? P of A given J and M being equal or not to P of A. So can we say that A is independent with M and J? We don't know. Okay. What about P of P? Can we say that B and G and M are conditionally independent on A? Yeah, okay. So I will show you that you can answer quite easily these kind of questions. I will not answer that yet. So you can answer these independence questions by looking at the topology. And so this is yet another example. If we have these three variables, x, y, and z, connected in a chain, so x connected to y and y connected to z, can we say, for example, whether or not x and z are independent? So what would you say for this one, this simpler one? Can you say that x and z are independent? Who thinks they are independent? One. Why? Yeah, but are they so necessarily independent? So in this case, obviously, they are not independent. Okay. So how can I show you that? So the question is whether or not x is independent of z. Okay. And so you can just take a counter example. Let's say we are in this scenario. We have three variables represented by these three capsules. X. You see the label there, x, y, and z. Let's say that x represents whether or not there is low pressure in the atmosphere. Then y corresponds to the rain variable. And z corresponds to traffic. Okay? So is x independent of z? The answer is no. And a counterexample is simply to say that low pressure causes rain, which itself causes traffic. And high pressure causes no rain, which causes no traffic. Okay? Any number that can be translated in this way. So the probability of rain given low pressure, let's set it to 1. And then the probability of traffic given rain, let's set it to 1. And then for the opposite value, let's say that the probability of no rain given high pressure is 1, and the probability of no traffic given no rain is 1. Okay? And so in this case, they are not independent. I see you all a bit puzzled. Yes?
I don't see how that's different from the questions you asked before.
Ah, that's the same. That's the same thing. So they are not independent. So they may. So that means they may be dependent. If they are not independent, they may be dependent. Right?
The question is like, can they be independent?
Can they be? Yes. Okay. So in this case, also because of this Bayesian network structure, what we would have, that's just because of how we organize the variables, the joint of the three variables could be rewritten as p of x times p of y given x times p of z given y. Okay? Now, what if we observe that it's raining? Can we say then that x is independent of z given y? Can we say that the probability of pressure or flow pressure given rain is the same as the probability of flow pressure given rain in traffic? Or can we say the probability of traffic given rain is the same as the probability of traffic given rain and low pressure? So if you observe that it's raining, can we say that x and y, pressure and traffic, are independent conditionally on the fact that you observe that there is rain? So in this case, the answer is yes. So what we need to show is whether or not these two variables are conditionally independent. Okay? So we can just fall back to the definition of conditional independence. And we said, if you remember last week, that, for example, the variable z and x would be conditionally independent on y if you can show that p of z given x and y is the same as p of z given y. That's just the definition of conditional independence. Okay? So in this case, we can arrive to this using the structure that we've assumed from the Bayesian network. So this conditional can be rewritten as the ratio of the joint p of x, y, and z over the marginal probability of x and y. Okay, that's just the definition of the conditional distribution. And then if we refactor the numerator using the structure of the Bayesian network, okay, we can rewrite the joint as p of x times p of y given x times p of z given y. And now what you see is that this term will simplify with this one will simplify with this one, and the only term which will remain is p of z given y. Okay? So in this case, we can show formally that yes, if you do observe y, then x and z are independent. Okay? And so we'll say in that case that the evidence, the observation, in this case through the range variable, will any evidence along the cascade, along the chain, will block the influence of the variables. Okay? So if you do observe that it's raining there, then we don't really care about the previous variables. We don't care about pressure anymore. Okay? Because the traffic in this Bayesian network is fully determined by the value of y. Okay? Regardless of the values of x. Okay? Okay, so if you have a cascade, can we say that x and z are independent? No, we can't. However, if we do observe an evidence along the chain, then they will become independent, conditionally on that variable that you observe. Okay, what about this other scenario in which we still have three variables, but they are connected together through a common parent? Okay, so we have x, y, the parent, and z, and both x and z share the same y parent. So for example, let's say the deadline for your project is at the end of the week. Okay, then you could model, for example, a scenario in which you have two other variables, whether or not you are using some forum to discuss among you, like a Discord server or whatever, and whether or not the lab is full if you have to do your project on computers. Okay? So in this case, what would you say about x and z? Can you say that x and z are independent? So intuitively, if the forum is busy, what would you say about the lab? Is it full or not? Yeah, it's likely to be full. Okay, so in this case, intuitively, and that's the correct intuition, you cannot say that they are independent. Okay, they might be dependent. Okay, and so that's exactly the counterexample there. The deadline could cause both the forum, or the server, to be busy and the lab to be full. And that's, again, something that you can instantiate formally by just considering these values for the probabilities associated to these events. Okay? What if you observe now that really the project is due by the end of the week? What if you observe the value of the common parent? What can you say about x and z? Are they conditionally independent now given their parent, or do they remain possibly dependent? Okay, so in this case, they would become independent conditionally on their parent. And again, we can show that. So what we want to say, so we want to show that P of z given x and their, so the two child nodes, P of z given x and its parent is the same as P of z given the parent only. In that case, if you can show that, then that would mean, again, by just the definition of conditional independence, that x and z are independent conditionally on y. Okay, so we can reuse the same logic as before. That can be written as a ratio of the full joint over the marginal of x and y. Then using the structure of the Bayesian network, which now is different, it's no longer a chain, it's a the common parent structure, that can be rewritten as py times p, so the marginal probability of the parent y times the conditional probability of the first variable given the parent times the conditional probability of the second variable given the parent. Okay? Similarly, you can rewrite the marginal over x and y as py times px given y. Okay, we are just using the product rule. And then again, you see that things simplify. Py simplify with py, and px given y simplify with px given y. And then the only term that remains is pz given y. So that shows again that in this case, z and x are conditionally independent given y. Okay? And in this case, we would say that if you have a structure like this, if you the observation of a parent will block the influence between the child nodes. Questions? Okay, the last case, and then we'll do a break, is the opposite of the previous one, in which we have two parents connected to a same child node. That's what we call a V structure. Okay, and so the question we'll be asking yourself is, what can we say about x and y? Are they independent? So let's say that in our scenario, x is rain, then z, a child node of x, is the traffic variable. But we consider another parent variable, which is whether or not there is a ball game, like or a soccer match or whatever you want tonight, which may also cause traffic. Can you say anything about x and y? Can you say whether or not they are independent? Yeah. Yeah. So as before, we can prove it. So I invite you to do the same kind of reasoning as here. It's not too complicated. And you should be able to show that these two variables are independent. Okay? Now, what if we observe traffic? What can we say about the rain and the soccer match? Are they independent, conditionally on rain? Oh, sorry, conditionally on traffic, or not? Yeah.
Probably. As in, if we observe traffic, there is a higher chance of observing either rain or that there's not an event.
So would you say that they're independent or
Dependent.
Okay. Okay. Yes. So in this case, you cannot say that they are independent. Okay. If you do observe the value of a child nodes, then they are no longer conditional. They are no longer independent. Okay. So another example, and I understand that it is very counterintuitive, but this is really true. Another example, let's say you are rolling 2 dice, okay, with 6 faces, whatever. I don't show you these 2 dice, okay, but I will tell you whether or not when I roll the 2, whether or not they hit the same number. Okay, and I just say you that, yes or no. Of course, the 2 dice are independent if I don't tell you anything. But if I tell you that yes, they are the same numbers, then obviously they become related to one another. Okay, they become statistically dependent. Okay, so observing in this case a child node will usually make these parent variables which are independent, unconditionally dependent in this case. Okay? Okay, let's take a break and we resume in, let's say, 10 minutes, around 9:40. Okay, we'll continue. Okay, so we've been talking about Bayesian networks, and then we were wondering ourselves if we could answer questions about the statistical independence of some variables. And we were covering a few base cases to start with. So the case of a cascade, so you have 3 variables connected to one another in a chain. If you take, so X connected to Y connected to Z, in this case, can we say that X and Z are independent? You can't say that. They may be dependent. However, we can say that they are conditionally independent, that X and Z are conditionally independent if you do observe any intermediate variable in the chain, in which case we would say that the evidence along the cascade would block the influence between the variables. Then we cover this other base case where we have 3 variables again sharing, where 2 of them share a common parent. In this case, again, we can't say whether X and Z are independent. However, we can say that they are conditionally independent if we do observe the value of their common ancestor. Okay? And finally, the third case was if when we have two parent nodes connected to a same child node, V structure, can we say in this case that X and Y are independent? And in this case, that's the opposite as before. Yes, we can say that they are independent. However, if we do observe the value of the common child, then they may become dependent. Okay? So now that we have these 3 base cases, we can actually use them to answer any questions about the statistical independence of 2 variables in a Bayesian network given 1 or several other variables. Okay? So the algorithm that we can use to do that is called D-separation. So if you assume that we have a complete Bayesian network with n variables, and then we ask ourselves, are 2 variables, let's say xi and xj, conditionally independent given 1 or actually several other variables? Can we answer these kind of questions? The algorithm is quite simple. So you consider all paths going from xi to xj. And this path, so any way, for example, if we consider L as xi and t as xj, we will consider any path that we can traverse to go from one to the other. And these paths, they don't have to be directed. Okay? So in this case, we would have one path, L to R to T. Okay? But there are other scenarios where we could have multiple paths. So for example, let's assume that we had another edge going from D to T, like this. Then we would have a second path connecting L to T, so L to R to D to T. Okay? So you just consider all these undirected paths, and if you find one or more active paths, then independence is not guaranteed. And on the other hand, if all the paths that you enumerate are inactive, then independence is guaranteed. What do I say by active or inactive paths? So I will define a path connecting two variables as active if each triple of variables that constitute a path is active. Okay? So a cascade A to B to C, where B is not observed, is active. Okay? So if you have a triple of variable like this, it's an active triple. Okay? Because the influence of the first is not blocked. The influence of the first on the third is not blocked by the second variable. Okay? If you have a common parent, so B as a common parent connected to A and C, where the parent is not observed, that's also an active triple. Okay? So if you if a triple constituting your path is like this, then it's also an active triple. If you have a V structure, like two parent nodes connected to same child nodes, and you do observe the child node, like in this case, then that's also an active triple. Or if you observe just a descendant of that child node, of that immediate child node, like in this case, so we have two parent nodes connected to a same child node, which we don't observe, but we do observe an ancestor of that child node. In this case, this is also an active triple. And the inactive cases would correspond to a cascade for which we observe the intermediate variable, would correspond to a common parent structure for which we do observe the parent, or a V structure for which we don't observe the child node. Okay? Now, given this, can you now answer these questions? Can you tell me whether or not L, the variable L, is conditionally independent with T prime given T? What would you say? How do we answer this question? Yeah.
Given T, it blocks the shape.
Exactly. So if we follow, so that's correct. If we follow the steps slowly, well, we have to enumerate all the paths from L to T prime. Okay. In this case, we would have only. So that's the same than here. We would have only one of them, so L to R to T prime. Okay. This path is made of 4 nodes, and it's made into two triples. Okay. So the first triple would be this one, and the second triple would be this one. Okay. And then the path would be active if all the triples in the path are active. But if one is inactive, then it's blocking the entire path. Okay? So L to R to T is a cascade. We don't observe the intermediate variable. It's active. Then we have R to T prime. It's a cascade as well. but we do observe T. Okay, so in this case, this one, the second triple is inactive. Therefore, the whole path is inactive. We had only one path. Okay, so we are in the first, we are in the second case. All paths, because we only have one in this case, are inactive. Then in this case, independence is guaranteed. Okay, and so yes, L and T prime are conditionally independent given T. Okay, let's take the second one. L, do we have that L and B are independent? Would you say yes? Would you say something else? Who would say yes, they are independent? 2, 3, yes. Who would say no? Who would say we don't know? Okay, so let's see. Okay, what are the paths connecting L to B? So there is only one here. It's L to R to T to B. Okay, it's made of 2 triples again. This one, and now this one. Okay, the first triple, L, R to T, is a cascade. It's active, okay, because we do not observe R. Then we have a V structure where we do not observe the child. So in this case, we don't, so we are in this scenario. So this one, the V structure, in this case, it's inactive. That means this path is inactive. Okay? And if all the paths are inactive, and again there is only one, then independence is guaranteed. Okay? So the answer, again, is yes. Let's take a third example. So the same as before, but let's assume now that we do observe T. What can we say? So now if we do observe T, we still have the same path, okay, made of the two same same triples, except that for the second, now we do observe T. Okay? So in this case, this V structure is no longer blocking. Okay? The V structure becomes active. Okay? So we are in a scenario where one or more paths are active. I mean, we again just have one path and it's active. So in this case, independence is not guaranteed. Okay? So in this case, the answer is maybe. And I say maybe because we can't answer whether or not they are independent, because now that would depend on the conditional probability tables that you associate to the nodes. Okay? But from the structure, the topology alone, we can't answer this question. Okay? Good. All right. So now let's move on to the second part for today, which is about inference. So now that we have defined probability distributions, and now that we have a compact or fully compact representations for this joint probability distribution, we can finally use them to do something. And when I say we want to use them, usually the kind of things you want to do with them is to query them. So to retrieve conditional probability distributions or marginal probability distributions from the joint probability distribution that these Bayesian networks do represent. Okay? So we could have simple queries, like what is the marginal probability of one variable given some evidence. Okay? And hidden there could be the fact that we are marginalizing out quite many other variables. Okay? We could also have conjunctive queries where we want not a marginal distribution, but a joint distribution now over a subset of variables given some observation. So these are the algorithms. We'll see algorithms to do that. Then later on, we'll see that we can also use this to do other things, like if you observe some evidence, you observe some observations, some values for some of the variables. Something you could be interested in is to retrieve the most likely explanation. So the most likely joint value of some set of query variables given some evidence. Okay, so that would correspond to the value Q, which maximizes the conditional probability of Q given. Okay, what we call the argmax of that function. Are you familiar with this notation, argmax? Yes, I see some yes, but I see some no's. Okay. Okay. Optimal decisions. We will also reuse that when we reach eventually reinforcement learning, in which we'll have to decide on some action A, which maximizes the expected value of the associated to the state that we reach. And you see there that to answer this question, we also need access to conditional probability distributions. Okay? Which could themselves be derived, for example, from a Bayesian network, let's say. Okay, so yeah, that's also an important remark. Every time I talk about reasoning in AI, what I really mean is that we will be talking about inference over some variables in the context of a probability distribution defined in some way. Okay? So reasoning and inference, for me, are more or less the same thing. Okay, so how do we do inference? We have seen last week already a first algorithm to do that, which I called inference by enumeration. So that's something very straightforward, which follows simply from the definition of a conditional and from a marginal distribution. So let's say we want to do the inference problem that we want to solve is to retrieve the conditional distribution of some query variable given the fact that you have observed a subset of size k of other variables, which we call the evidence variable. Okay? But in your model, you also have other variables, hidden variables, that you include because you think they are important, but unfortunately, which you don't observe. Okay? So how do we then go from the joint over all the variables, so the query, the evidence, and the hidden variables? Well, that's easy. If you start from the table representing this joint distribution, you just select the entries that are consistent with the evidence. Okay, you select all the rows for which the evidence variable correspond to the values that you are given. Then you marginalize out all the hidden variables to obtain a joint distribution over the query and the evidence variables. Okay, so the joint over the query and the evidence variables at those values will correspond to the sum of the probability tables corresponding to the variable Q for the values when you enumerate the values for the hidden variables and you condition on the values that you're given for the other variables, the evidence variable. Okay, so now we have a joint over a subset of variables, and then we need to obtain the conditional of Q given the evidence variable, which we simply obtain by marginalizing out the query variable. That gives us access to the normalizing constant. And then if you take these probability values, you divide them by this normalization constant, then we obtain the conditional of Q given the evidence values. Okay? What if we don't have a full joint probability distribution instantiated as a big table, but we have instead a Bayesian network which represents this probability distribution? So let's reconsider once again the same setting as before with the burglar, the earthquake, the alarm, and the two neighbors. And let's say we want to solve this inference problem. So the probability, we want to obtain a probability of a burglar given John and Mary. Okay? So we know, if you just follow the previous algorithms, that we have to select the entries that are consistent with J and M, okay? And then we have to marginalize out all the hidden variables. In this case, the hidden variables, they correspond to the earthquake and the alarm. Okay? So that means this is equal to, we marginalize out the earthquake, we marginalize out the alarm, and we have P, B, J, M, E. Okay? Where Z is the normalization constant. Okay? In the slide, sometimes you will see that I'm a bit lazy, and instead of writing this, I just remove it. And instead of having an equal, I will just use this symbol to say that it's proportional to this. Okay, so that means proportional to this quantity by some factor which does not depend on the values of the variable. Okay, so this is a constant that we can just compute once and for all. And then if we want to go from these values to actual probability values, then we just have to divide these numbers by the normalization constant, and we would fall back to proper probability values. Okay? Now, if we say that we represent our probability distribution as a Bayesian network, then for this particular structure, that also means that this can be rewritten we can rewrite this joint following the topology of the Bayesian network, in which case we would have PB, PE, PA given B and E, PJ given A, and PM given E. Okay? Okay, and if you do that, then you would obtain. Now, if you implement this in Python and implement this sum exactly in this way, you would obtain exactly the values that we want to retrieve. Okay? Do you see any issue with that? So it's correct, but do you see any issue? Yeah.
P of A given B, because we don't know the values.
Hmm?
Maybe we don't know the value of B.
Sure.
So P of A given B would be plus E would be difficult to retrieve.
Yeah, but these are probability distributions too. So these things are tables. Okay. You see the bold P. So this is a table. This is a scalar. This is a table. This is a scalar. This is a scalar. So when I say this, it means that I have to enumerate all possible values of B. And similarly there, I have to define the condition of A given the first value of B and E, and also given the second value of B and E. Okay? Well, that's not an issue. Do you see any computational issue? Yeah.
The number we obtain might be really small.
Yeah. Okay. Sure.
No problem for
No, it's not really a problem. I mean, it can be a problem, but that's not what I want to discuss on.
if we compute the full probability table, it's a square, and it's a square function. So it's going to be very limited.
Where is the square function here?
Well, there are two sums, so you have to sum over A for all E.
Uh-huh.
Have two loops.
Yeah, but I don't think we'll be able to escape these two loops. The main issue is that if we write this computation exactly in this way, and if we execute it in this way, well, we would have to compute this product of 5 terms, which basically would amount to reinstantiate the full joint probability table. Okay, so that would be exponential in the number of variables, and then we would iterate with these two loops around it over the rows. Okay, so effectively the memory requirements and the time complexity would be now would be exponential in the number of variables. Okay, so even though we have a compact representation to solve this query in this way, we would rebuild the entire enlarged joint probability distribution, and that's simply inefficient. Okay. So what we can do instead is to notice that there are terms inside these products that do not depend on E and A. Okay, so we could factor them out of the sums. Okay, so in this case, this could be written. So we see that B does not depend on either E and A, so we can just factor it out. Okay. Then we have P of E, which does not depend on A, so we can put it in between Then we have P of A given B and E. It depends on both E and A, so that remains inside. And then we have P of J given A, it depends on okay, and now if we implement this computation following this expression, we don't have any longer to reinstantiate the whole exponentially large joint distribution table. Okay? The largest term would certainly correspond to this one, where we have to join these three values together. Okay? But not all the variables together. Okay? So in the slides, what I say is that the factors that do not depend on the variables in the summations can be factored out, which means that marginalization does not necessarily have to be done at the end. You can marginalize some of the variables, not at the end, okay, as we outline in the algorithm, where first we join everything, then we marginalize out. Okay, you can marginalize before or after. I mean, you can mix the join of several factors with marginalizations. Okay. So in terms of algorithms, you would arrive to this, which is still the inference by enumeration algorithm, where we just apply this trick, where we factor out some of the variables outside of the summations. It's not really interesting. And the issue with this algorithm is that even though we are a bit smarter, there are still computations that we have to redo. So even in this version of the computation of P of B given J and M, this can be rewritten as a tree, okay, where we have P of B that would be the term at the outside of the sum. Then P of E plus, so we would have the sum over two values, E and not E. And then for each of those, we would have a sum over E and not B. And then we would multiply together all the remaining conditional probability tables. Okay? And what you see in this tree is that there are branches which are exactly the same. So if you look at this branch here and this one, they are the same. So that means we would be computing these two products twice, which is a bit silly because we are wasting resources. And similarly here, this part of the tree is the same as this one. Okay? So even though we factor out some of the terms, it's not fully optimal, fully efficient, because there are still repeated computations. What we would need to avoid these repetitions, repeated computation, would be to store intermediate results. Okay? So if we had stored these results, then we could notice that we have to recompute it once again, and we could just use the value that we have computed before instead of recomputing it from scratch. Okay? So that leads us to another algorithm, which we call inference by variable elimination. And basically, the idea of this algorithm is to carry out the sum, the various summations that we have in this expression from right to left instead of left to right. Okay? And if we do it from right to left, then we would have a chance to store the intermediate results that we need to continue the computation. Okay? And so the idea is to join subtable and then to eliminate hidden variables, and then you alternate between these two things. So quickly, the algorithm goes as follows. I'm going a bit faster over all of this because honestly, this is not very useful in practice. But I think it's important to show you that even though you can make this computation and you can do them exactly, the computation you will have to do at the end of the day remains exponential. That's what we'll arrive to at the end. Okay? So variable elimination, let's say we want to solve this query, P of Q given some evidence. Then the way we would do that would be to start with what we call initial factors, which correspond to the conditional probability tables that you instantiate by the evidence value. And then you would repeat this loop in which you pick one hidden variable that you have not yet removed, that you have not yet eliminated, hence the name of the algorithm. Then you list all the factors that do mention this variable. You join them all, so you multiply them all together, and then you sum out H, so you marginalize it out of the distribution that you have just produced by joining all the factors. You repeat that until you don't have any hidden variable left, then you join all the remaining factors, and then you normalize. Okay, so before I show you an example, what I mean by a factor, let's say call it F, is a multi-dimensional array, so tensor, for example, indexed by the value of its argument variables. So for example, we could have a factor about this part of the Bayesian network, so the value of J given the alarm, okay? And we could define a factor which is a function. Let's say we do observe John, okay? So John is fixed to its positive value. Then the value of the probability will only depend on the value of the parent, so A or not A, okay? So in this case, we could define a factor, in this case as a one-dimensional array, taking two values, because we have two values for the variable A so the parent variable, A or not A. And the first entry would be P of J given A, and the second would be P of J given not A. Okay? And we would store these numbers. All right? Does that make sense? these numbers, they don't have to sum to 1. Huh? It's not a mistake. Okay, because here we are just enumerating the probability values of j being positive as a function of the value of the parents. Okay, and not the opposite. We don't fix the parent and then enumerate the probability values of the joint variable. In which case, yes, they should sum to 1. Okay, but we are in the opposite scenario. Okay, you can extend that to 2, 3, n dimensional arrays. Okay, and then in this step, what I say is that you should join factors, mentioning some variable. What do I mean by joining factors? So let's say you have 2 factors f1 indexed by the values of 2 variables, a and b. That's for the first factor. And the second, which would be a factor representing probability values for b and c. Okay? And these are the numbers that you associate to all possible combinations of these 2 variables inside these factors. When I say I want to join f1 with f2, basically what I want to do is to produce now a new factor which would include all the variables that we find in the 2 factors. So the variable associated to this factor would be the union of the variable associated to the 2 individual factors, so a, b, and c. And then we have to compute the corresponding new values, which correspond to all the combinations, and then you multiply all the probability values. So basically what we are just doing is some kind of join between these 2 tables, exactly like in a database. If you have in a relational database, you have 2 tables, and then you join them on some attribute, on some variable. You obtain a new variable, which is defined, for which the columns correspond to the union of the variables in the 2 first tables. That's exactly the same concept, except that now the values that we associate would correspond to the product of the respective probabilities. Okay? So that's for the joint, and then elimination. So if we say with a factor defined on 3 variables, a, b, and c, okay, which, for example, could be encoded by this part of the table. So that's a factor with 3 variables. So that's, in this case, a 2 by 2 by 2 array. It's a 3-dimensional array where each of the 3 dimensions can take 2 values. Okay? We can remove or eliminate some variable, let's say a, from this factor by simply enumerating all subtables, one for each of the values of the variable that we want to eliminate. So we need to sum over all the values that the variable a can take, and then we would sum together all the subtables that we select. Okay? So in this case, we would just sum together the 2 tables that we get by first setting a to its positive value and then setting a to its negative value. Okay? And so we would have now these 2 sub-arrays that we sum together, and we would obtain now this new factor. Okay? So we can do that. We can run this algorithm, let's say, for the same alarm network. So let's just do it to be complete. Okay, I'm sorry, but there is nothing to erase in this classroom. And I have only green and blue chalks. Or maybe I can do it here. Okay, so let's say we want to do again the same query, but now using variable elimination. Okay, so by just running, by following the topology of the network, we know that that's proportional to this. Okay. So the first step is to instantiate in this algorithm all the factors. In this case, I would have 5 factors. I would have this one, f1, which values can be indexed by the values that b can take. So it would be a function of b. Then we would have this one, f2e. Then we would have this one, which is a factor which depends on 3 variables, a, b, and e. We have this one, which is fourth factor, which depends on a and j. And then fifth factor, which depends on a and m. Okay? Except that I do observe j and m, so this is not really a function of j nor of m. Okay, I can just freeze these values once and for all and be done with these 2 variables already. Okay, and this can be written as f1 b that you join. Okay, that's not just a regular multiplication, it's the join. By summing again all the variables, all the values of the earthquake variables. So E now, I access this value E in F2 times joint with A, F3, A, B, E, join with F4, A, join with F5, A. Okay? And now we have to run the algorithms. So we have set all the factors initially. So these are these 5 ones, F1, F2, F3, F4, and F5. Okay? And we have 2 variables to eliminate. We have the 2 hidden variables. One is for the alarm, and the other is for the earthquake. Okay? So we are free to decide in which order we eliminate them. So let's say we want to eliminate A. Then the algorithm says that you should just select all the factors in which A appears. Okay, so in this case, you should select F3. You should select F4. And you should select F5. Okay, because these 3 factors do depend on A. Okay, you join them all together, that produce some distribution, and then you eliminate out the variable A by just summing all the submatrices, all the subarrays for each of the values of A. And that produces a new factor, let's say F6, which is now a function of B, because B is still there. So, I mean, this product here is depends on the union of the variables in the factors. So in this case, the union of A, B, E, A, and A. So that's A, B, E. Then we remove A. That's only B and E. Okay, so that means now P of B given Jm is proportional to, so this thing which has not changed, E F2E. But this thing now we have joined all of these factors together and we've eliminated A. Okay, that gives us F6. No, oh, eliminate A. Okay? Then we have to continue. We still have one inner variable, E. Eliminate E. We select all the factors that in which E appears. So we have F2. We have this one that no longer exists, but we have F6 now, in which there is E. We join them. We eliminate E. And that gives us a new factor, F7, which depends on B. Okay? And because of that, now we have that P of B given J and M is proportional to F1B times F7. Okay? And we are done. Now we just have to join these two things. That will give us the conditional property, an unnormalized conditional probability distribution of B given the evidence that we have set. And then we normalize these values and we get the answer that we want. Okay? Okay, so this is just for your own education. We'll not ask questions about that. You can simplify, blah, blah, blah. But what is important to notice is that and this is a slide that you should really understand to see why these algorithms are a bit pointless. The efficiency, the time or the memory efficiency of this algorithm will depend on the ordering that you pick to eliminate the variables. Okay? Because depending on the ordering that you pick, when you join all these factors together, you may or may not have to build a large and possibly very large new factor. Okay? And so this is a degenerate case in which, let's say, we want to do inference on this variable given that you observe all these ones. Okay? So in this case, the hidden variables would be z, x1, x2 up to xn minus 1. And then it's interesting to see what would happen if you eliminate these hidden variables by following this ordering, z first, then x1, then x2, then xn, or x1 first, then x2, then xn minus 1, and then finally z. What would happen is that in this ordering, when we eliminate the first variable z, we would be joining together many, many, many factors, and that would be proportional. I mean, the resulting new factor would have a size which is exponential in the number of variables. So, yeah, we are back to the same problem. It remains inefficient. However, if we could identify the ordering which leads to the most compact factors along the computation, then, and this is one of those in this case, then the largest size of any factor, in this case, would remain, in this case, proportional to 2 to the 2, so very compact. Okay? So basically what happened is that the complexity of this algorithm is entirely dominated by the size of the largest factor that you have to build when you run the algorithm. Unfortunately, there is no known algorithm to find this optimal ordering. That's something we can show to be NP-hard. Okay? So that means there is no known, at least today, no known algorithm that would run in polynomial time and that would be able to find this optimal ordering. Meaning, today in 2024, we have no better algorithm to identify this path than something which is exponential. Okay, so we have not gained anything. If you have any idea, please do so, but that's a very tough problem. But yeah, if you find a solution for that, then you will become very famous and you will get campus to your names and other things. All right, so that means for now we don't have satisfactory solutions. What do we do then? Well, then what we should do is to maybe make peace with ourselves and say that, okay, I will not be able to do exact inference. It's too costly. However, maybe it's good enough to just have approximate results to approximate the correct answer. And that's usually what we do in AI or in all these probabilistic problems, all these inference problems. We run algorithms that are only approximate. We can make them asymptotically exact, which is good enough, but we don't have efficient and exact algorithms. So there are various families of algorithms that you can use to solve these inference problems only approximately. You have sampling methods like Markov chain Monte Carlo and other algorithms where the trick is to produce answers by repeatedly generating random numbers, random realizations from some distribution of interest. That's quite efficient. We'll not see any of those except the last one in this course, but MCMC algorithms are very useful in many, many problems. Variational methods in which we reformulate the inference problem as an optimization problem, so then it becomes as efficient as just optimizing a function, which is itself quite complicated, but we do have now efficient algorithm for that. We'll not see any of those, but that's something we'll use, for example, if some of you reach this class, when we do talk about deep learning in the master program, basically all generative models, so this neural network that you see to generate images, for example, all of them are based on variational methods. There also exist other families like belief propagation, which are a bit older, where you formulate inference as some kind of message passing algorithm. And finally, machine learning methods, in which you directly approximate the target distribution. So for example, the distribution that you're interested in, like P of B given J and M, as a machine learning model, for example, with a neural network. Okay? Questions? Okay, but that's the main message. Basically, exact inference is difficult. We don't have any efficient algorithm for that. Okay? All right, now let's move on to the last part for today, parameter learning. So far, we have assumed that we are given this Bayesian network and we are given these probability values inside the tables. So you may wonder, when you have to build such a model, how do you obtain these values? Maybe your knowledge is not good enough to put appropriate values for these numbers. So how do you do that? So a workaround to that is, instead of saying that we have a fixed probability distribution a priori over all the random variables in our problem, then what we'll assume is something a bit more generic, which is a parameterized family. So it's the same Bayesian network, it's the same probability distribution, but now which we parameterize in terms of parameters that we'll have to figure out later on. And these parameters could be, for example, the values that you associate to each combinations, for example, of your variables. Okay, like really the entries of the probability tables. Okay. So usually that would be much simpler because then the only thing we'll have to worry about is the general structure. And basically the assumptions, like the conditional independence assumptions that we are making. Everything else will parameterize out. And then we'll say that, okay, but maybe I also have access to some data, to some data sets, so realizations of the process that I'm trying to model. And I will then fine-tune or adjust the parameters of my parametric family, Px given theta, such that the data set that I have is well explained by the model that I consider. Okay? So let's take a concrete example. Let's take this one. So let's say we are modeling a distribution about candies. Okay? And you may have two flavors about the candies. I don't know, strawberry and raspberry. Okay? So you can model that as a very simple Bayesian network in which you have only one variable, okay, which is the flavor, which is this random outcome. If you pick a candy out of the bag, you will get one of these two flavors. Okay? And you can model that in this way. But your knowledge is limited. You don't know the proportion that you should associate to each outcome. It could be 50-50, it could be 60-40, it could be 99-1%. You don't know. Okay? Now, but let's say you actually get the chance of observing this process, so you get access to some candies. Can you use these observations, these realizations, to figure out a good theta value, so in this case, a good marginal probability, for example, for the cherry flavor in the bag? Can you do that? How would you do that? So let's take an example, actually, the bag with candies. Okay? So take one of them. You don't get to see them. Okay, what's the flavor? Raspberry. Or strawberry. No, strawberry, this one. Okay. So we have one outcome, one realization. Could we use this information to inform the value that we should set for theta, which is these unknown proportions of one or the other flavor? Why not?
Because we don't have a lot of data.
And why is that an issue?
You could estimate, but it wouldn't be a good estimation.
Okay, and how would you estimate?
Well, if it's a strawberry, then you could estimate it to 1.
Okay, you could say that I believe that the marginal probability of strawberry flavor is 100% because in all the observations that I collected, for all of them, I saw only strawberry. Okay, what if you pick another one? Any one of you? Raspberry. So how do you update now this knowledge? What do you do with this second realization? How do you set theta now? Would you say it's 100%? Or would you make another guess for theta? 50-50, okay. Third one. Raspberry, I think. Okay, so we have two strawberries, two raspberry, one strawberry. How do you use that now? How do you update? So what value of theta do you decide to put inside your probabilistic model? 1/3, okay. Once more.
It's raspberry.
Raspberry again. Strawberry. So we have 3 raspberry, 2 strawberries. Once more. Strawberries. Okay, let's go here. Strawberry. I'm sorry for those in the middle. Okay, and one last. Okay, so how many strawberries do we have? Can you raise your hand for the strawberries? So 1, 2, 3, 4, 5. And for the raspberries, 1, 2, 3, 4. Okay, so 4 and 5. How do we use these numbers to inform the choice of theta? So several of you said, okay, I will use the ratio, like, so I don't know which one is which anymore, but let's say this could correspond to strawberry and this one to raspberry. So we have a proportion of 4/9 for the first and the complement for the other, okay? And so if we want to model that, we could just maybe set this proportion there, okay? Okay, can any one of you tell me why we should do that? Yeah.
Distribution uniform.
Sorry?
We assume the distribution to be uniform, so the theta would be just a ratio. Because if you have to take something like a normal distribution or another distribution, you'd use the parameter of the distribution.
I'm not following.
But, the theta would be the parameter of some probabilistic distribution.
Yes.
Which in this case we assume to be linear distribution.
It's not, there is no linear distribution.
Uniform. Uniform distribution.
It's not uniform. We just have two outcomes. Strawberry and raspberry. It's a binomial distribution. Okay, and we have to set the parameters of this binomial distribution, which is the proportion of, let's say, the positive outcome, or the cherry flavor, or the strawberry flavor, whatever. Okay, but why should we set this value theta to this particular ratio? What's the rationale that you are following to do that?
It's the empirical value of the probability. You have the sample size and you.
Okay, that's a fact. I want a reason. Why should you use that?
Because it's the only data that you have to infer the probability. Therefore, the best guess you can make is by estimating the probability over your sample size.
To me, it looks more like an opinion, but okay.
It's the most accurate one.
Why?
It's the closest to reality.
Maybe, maybe not. I don't know. Yes.
Maximizes the likelihood of this happening.
Yes. So the principle that we are actually following is the one of maximum likelihood estimation. Okay, and everything that you said are just consequences of this principle. Okay, they are not the cause; they are only the consequences. So in general, if we have a data set of, say, D observations from 1 to n, like these 9 outcomes for the flavors, and if we assume a probabilistic model, which is parametric, depends on parameters for which we have to set the value, then when we define this parametric model, we actually define the likelihood of the data set given the parameters. Okay? If we assume that these observations are ID, so they are identically distributed and independently distributed, then this probability over a data set can be written as a product of the marginal probabilities of the individual outcomes conditionally on the parameters. Okay? And then one very reasonable principle would be to pick a value of theta for which the probability of the data set is the largest. Okay? That's called maximum likelihood estimation. You pick as parameters values such that the likelihood of your observations are the largest. Okay, so in practice, how do we do that? Well, that's something we can't do always, but for these very silly problems, that's something we can do. We express the log likelihood, so as a function, so the data set is fixed. It's now just a function of the parameters, and we want to find good values for these parameters. So you write down the log likelihood as this function L with theta as an argument, which is the logarithm of the likelihood, the probability of the data set for the parameters values theta. Then you differentiate, so you write down the derivative of this log likelihood function with respect to the parameters. And since we want to find the parameters for which the likelihood is the largest, okay, it will be the same for the log likelihood. We want the log likelihood which is the largest, which will happen at some maximum of that function, at which the derivative is equal to 0. Okay, at a maximum, the derivative of the function L will be equal to 0. Okay, so then we have to find the parameter values theta star such that the derivative are 0. Okay, maybe you should also check that this is really a maximum, which you can do by checking whether or not the Hn of L is negative definite. Okay, so in the first case, with this very simple problem where we want to estimate or we want to set a value for the proportion of candies of one flavor. So let's say, if we follow this principle, we have a data set D of realizations, which depends on some value for the parameters. We assume that these observations are ID, so we can write this as a product of marginal probabilities, P of xj given theta. And if we assume this distribution, a Bernoulli distribution, then it's as if we were saying that, let's say we have C, in this case cherries, or C strawberries, and then we have N minus C for the other flavor. Okay, then the probability, in this case, of this product, the joint probability would be equal simply to theta to the power C, because we have observed that C times 1 minus theta to the power L, because we have observed the other flavor L times. Okay, and this other flavor comes with a probability of 1 minus theta. Okay, so that's the likelihood. We can then express the log likelihood, take the logarithm of these products. So the logarithm of these products become a sum of logarithms. Then we have the logarithm of, let's say, theta to the C. That becomes C times log theta. And similarly for the other part, which becomes L times the logarithm of 1 minus theta. Okay? Then you differentiate with respect to the parameters. Okay? So you take the derivative of this expression with respect to theta. That gives us this expression, C over theta minus L over 1 minus theta. You constrain this to be equal to 0. You solve for theta, and you would find that, yes, theta should be set to the empirical proportion. Okay? So this is what you suggested, which is correct. But what I want you to understand is this is just a consequence of the maximum likelihood estimation principle under the model that we have considered. Okay, for everyone? There was also this other setting where we still have two flavors, cherry and lime or strawberry and raspberry, whatever you want, but the wrapping, the color of the wrapper may change, but supposedly it still depends on the flavor of the candy. Okay, so we could have that if we actually have a cherry flavor, then the probability of a red wrapping for a cherry flavor would be theta 1 to be found, and the probability for the probability for having a red wrapper but a lime flavor would be theta 2. Okay. So now we have three parameters instead of one. Okay, but again, we can use a data set of observations. In this case, we would observe two variables every time, one for the flavor F and another for the color W. Okay? We can do the same thing, in which case we would have a likelihood which is a bit longer, but which is just a product of all these things. So let's say we do observe C flavors of the first kind and then L flavors of the other kind. So they would have together a joint probability of this, and then these terms correspond to the probabilities associated first here to the probability of having a red wrapper for one or the other flavor, and the probability of having the other color for one or the other flavor. Okay. So again, you can take you define the log likelihood. This simplifies into the sum of terms. You differentiate with respect to the parameter theta. In this case, we have three parameters, so we have to differentiate with respect to each of those. So we take the derivative of L with respect to theta, with respect to theta 1, and with respect to theta 2. We get now a system of equations, which we can constrain to be equal to 0. Okay? And then we have three equations, three unknown. We solve, and we get these values. Okay? Okay, then there is this interesting observation, which we've already discussed very quickly. What if we unwrap, or what if we only observe one candy? How does that affect the quality of the parameters that we'll set in our probabilistic model? So if you have only one observation, and we consider the very first case where we just have one parameter to guess, then the theta value that we would then put inside this table would be either 100% or 0%. Okay? That's consistent with the maximum likelihood estimation principle. That's what you should do. Would you do that? Would you feel comfortable in using these values? Why not? There are not enough observations. And in this case, where there are not enough observations, on what else could you rely?
Just all or guess.
Yeah, or guess. So you may have prior knowledge, okay, which could maybe you should or could fall back if you don't observe, if you don't have sufficiently many observations. Okay. If you want to do so the risk, basically, if you have small data sets, then maximum likelihood estimation will lead to what we call overfitting. It will explain the data very well, but then if you want to apply the same probabilistic model to new data, which supposedly comes from the same data generating process, then certainly your model would not be very good because it's fitting your very small data set too well and will not account for the unobserved variability of the actual data. Okay? Second, the MLE, the maximum likelihood estimator, does not also provide any measure of uncertainty about the parameters. You just get a value, but you don't know if you should trust or not this value. So you can do something else, which is to adopt a Bayesian attitude toward the problem and say that instead of having parameters that are just numbers that you fix once and for all, you may say these parameters, I may have subjective beliefs about them, so you have initial guesses, okay, and I also want to characterize the uncertainty that remain about these parameters. Okay? So the proper way to do that is as before, you can just say, this uncertainty, I will model that with probability values, And so I will upgrade now theta from just static parameters to random variables. And this is where maybe it can be confusing for you. This theta will be random variables, not that they are random and contribute in some kind of stochastic way in what you eventually observe, but you use random variables simply to acknowledge that you have uncertainty, okay? And the proper way to model this uncertainty is by having them as random variables, okay? Okay, now if you upgrade them to random variables, then we should also associate a prior, okay, or initial guess, as you said. So prior distribution, let's call it p theta over the parameters. And then now as we collect data, as we get to observe realizations, instead of fitting the parameters, what we'll do instead is just to update our prior beliefs with the data that we collect. Okay? And so what we'll have to do is to solve an inference problem in which we want to recover the conditional distribution of the parameters given the data. Conditional distribution of variables that you want to query conditionally on a few variables D that you can observe. Okay, so if we take this example with the strawberry and raspberry flavors, we could say that, okay, now theta becomes a random variable. I have to set a prior my initial beliefs. Okay, you could say that it follows a beta distribution of parameters A and B. So beta distribution is a distribution over continuous variables, in this case, but continuous variable limited to the segment going from 0 to 1. Okay, because this proportion is a value between 0 and 1. So we should have a probability distribution over that interval only. It would make no sense to say that we have a Gaussian beliefs about this variable because the Gaussian distribution would spill out outside of the 0-1 interval. You can use a beta distribution instead. It depends on two parameters, A and B. Okay, and the probability, the probability density that we associate to each continuous values theta now takes this form. Okay, and basically when you set A and B to 1 initially, you will get a uniform distribution over the interval 0, 1. Okay? Okay, so now what if we get our first observation, we get a first flavor, let's say cherry, then we want to update our prior beliefs given this cherry flavor, so we have to compute this posterior parameters given cherry. So how do we go then to this expression? So how can I rewrite the posterior using the terms that I have? Which usually, we would have in this case, so initially we had this very simple and degenerate Bayesian network with one variable, okay, to which we associated a probability distribution, PF, okay, in which inside we have this table PF equals cherry, and then we said it's equal to theta, okay? Now, in the Bayesian case, I will say that I have another variable, theta, okay, which will be connected to F. And now I also have, so now it becomes this. And now here I have a prior distribution, which I say is a beta distribution, okay, over theta. Okay, so we do observe F, and we want the posterior on theta. Okay, we observe cherry, but we want the conditional of the other variable theta given cherry. How do you do that? How do you go from the left-hand side to the right-hand side? Yeah. Yes, you use the Bayes rule. Thank you. Okay, so you can rewrite the posterior as something which is proportional to the prior times the likelihood. Okay, here it's proportional, so you should also include the evidence P of cherry. Okay, but let's just say we'll have something which is proportional. Okay, and then now we just replace the prior and the cherry by their expressions, which we have put there. Okay. This is what we have in the Bayesian network. So the prior is this beta distribution, and P of cherry given theta is theta itself. Okay, that's this entry. Then we replace the prior by its own expressions. Okay, then you can reshuffle a bit the terms. You get this, and what you get is that the posterior is itself a beta distribution, where you have seen one more occurrence of the positive class. Okay, so this A and B basically represent the number of occurrences of first the positive and then the negative class. So let's keep this. Okay. Then finally, maximum a posteriori estimation. So there will be many cases where you can't compute the posterior. Okay, you can always use the Bayes rule, but at some point you may be stuck, and you may not have a closed form expression for the posterior itself. Okay, so in this case, again, you will have to resort to approximations. One of them is to say that instead of just considering the whole distribution, the whole posterior distribution, you will approximate this whole posterior distribution with one number. Okay, and one possible number would be the most likely outcome out of that posterior distribution, which is what you call the maximum posteriori. Okay, so you summarize the posterior distribution by its point estimate theta star, which is the theta value for which the posterior distribution is the largest. Okay? So that's the Bayesian equivalent of the maximum likelihood estimator. And actually, the two of them correspond to the same thing when you start with prior beliefs. When you start with uniform prior beliefs, in which case this term would be the same for any value of theta. Okay, and so the maximum posteriori estimate, P of d given theta times P of theta would be the same as the maximum of P of d given theta only, because this does not really depend any longer on the value of theta, since the uniform is the same for any theta, so it's just a constant. And so the value that maximizes the posterior or the likelihood are the same. Okay, in this case, the MLE and the MAP would be identical. But if you have prior beliefs that are not uniform, okay, then the answer would not coincide. They would have asymptotically correspond to the same thing as you get, on the other hand, more and more observations. As the size of the increases, the weight of the prior would become less and less, and they would also, in this case, converge to the same estimate of theta, the same estimate theta. Okay, questions on this? So I see that it's a bit late, so I will not do the demo, but I invite you to check. There is a notebook on the GitHub repo. It's called cherries.ipython notebook. You can run it, and you will see this being applied on that same problem. When you start from some prior beliefs, you observe some data, and then you update the prior, and you'll get the shape of the posterior as you get more and more observations. And you will see how it matches or not with the MLE, and also you will also see how you approximate it with the MAP. All right, so to summarize for this morning, a Bayesian network fully specifies a full joint distribution, but the main interest, the main point of this structure is that they are more compact than just using the full table. They may also make independence assumptions explicit, okay, and specifically conditional independence assumptions between random variables can be made and are explicit in a Bayesian network. They are represented by all the edges that you don't see. Inference now is the problem of computing a marginal or conditional probability distribution from a joint. Okay, exact inference is possible for simple distributions, for discrete distribution, but we don't have any efficient algorithm for that. So basically, beyond brute forcing the solution, we don't know any better algorithm. So it's exponential in the number of variables. However, we can use approximate inference algorithm instead. Okay, we'll not see them in this course, but that's something we'll cover later on. And usually, you will get good enough answers with that. And finally, and that's very important, you can parameterize the distribution, for example, in the form of a Bayesian network, by adding parameters, which then you have to fit, you have to calibrate. And one way to fit these parameters is to follow, for example, maximum likelihood estimation, in which you would pick the parameters for which the data is explained the best under your model, or in a very pure Bayesian way using Bayesian inference, in which case you would make these parameters random variables. You would have prior beliefs about them. You would have uncertainties. Okay, and then you would do the fit, not by optimizing parameters, but by simply doing a Bayesian update where you go from a prior to a posterior. Okay? All right. Questions, comments? Okay. I recommend that next time you come very fresh because the next lecture will be quite important. We'll start mixing the two previous lectures together to be able to reason over time. So we'll consider environments that are probabilistic, stochastic, and also evolve through time. And we'll try to see how we can estimate the state of the system, which we don't see, but we can estimate as it evolves through time and as we collect observations. And that's something you will have to then implement in the second project. All right, so now the exercise session, we can resume at 11:20.